Every atom you've ever touched, every breath you've taken, every star you've looked at on a clear night, all of it is made of the same basic stuff. Matter, protons, neutrons, electrons, arranged in different configurations to make everything that has ever existed. That feels like the most obvious fact in the world. Of course, the universe is made of matter. What else would it be made of? Here's the crack in that. When physicists work out what the Big Bang should have produced, the answer isn't a universe full of matter. The answer is nothing. The equations say that when the universe was born, it should have created matter and its opposite in exactly equal amounts, and those two things should have found each other, collided, and destroyed each other completely, leaving behind a universe of pure energy and no physical substance at all. No stars, no planets, no you. The fact that you exist is, from a physics standpoint, a catastrophic anomaly. And right now, in a facility buried under the Swiss-French border, scientists are trapping the rarest substance ever made, studying it atom by atom, trying to figure out why the universe broke its own rules in your favor. The opposite of matter is called antimatter. Every particle that makes up ordinary matter has a corresponding antiparticle with opposite charge but otherwise identical properties. An electron has an anti-electron, called a positron. A proton has an antiproton. When a particle meets its antiparticle, they don't bounce off each other, they annihilate. Both particles vanish in a flash of pure energy. It's not a violent explosion in the movie sense. It's more like two waves on water that are perfectly out of phase, cancelling each other to a flat surface. The physical reality just ceases. Think about what that means for the Big Bang. Physics says the energy that created the early universe should have produced particles and antiparticles in matched pairs, like a factory stamping out tiles and mirror image tiles at the exact same rate. The prediction is a 50-50 split, matter and antimatter, and a universe where everything immediately destroys itself. Instead, we got this: everything. The question physicists have been losing sleep over for decades is what tipped the balance. Something in the first fraction of a second after the Big Bang must have given matter a tiny advantage over antimatter. The universe we live in is the leftover residue of that advantage. For every billion antiparticles that got made, there were 1,000,000,001 matter particles, the pairs annihilated. The one leftover particle in a billion survived. Every star, every galaxy, every atom in your body is one of those survivors. That ratio is terrifying when you sit with it. In 1967, a Soviet physicist named Andrei Sakharov laid out exactly what conditions would have to exist for matter to win that fight. His argument was precise. Nature would need to treat matter and antimatter differently. Not dramatically differently, just slightly. Just enough that matter had an edge. He called it a violation of something called CP symmetry, which basically means the laws of physics would have to behave differently for a particle than for its mirror image antiparticle. If CP symmetry holds perfectly, matter and antimatter are truly interchangeable, and the universe ends in mutual annihilation. If CP symmetry is broken, matter gets an advantage, and here we are. 3 years before Sakharov published his conditions, 2 American physicists had already accidentally stumbled onto the first evidence that CP symmetry does break. In 1964, James Cronin and Fitch were studying particles called kaons, unstable particles that can decay in different ways, and they found that kaons and antichons didn't decay at exactly the same rate. The mirror wasn't perfect. CP symmetry was violated. They won the Nobel Prize for it in 1980. That should have solved everything. CP symmetry breaks. Matter gets an advantage. Universe exists. Case closed. Except the numbers don't work. The amount of CP violation that Cronin and Fitch found and that physicists have measured since is far too small, by a factor of roughly 10 billion. The known CP violation in the Standard Model can explain maybe a billionth of the matter excess we actually observe. It's like explaining how a river formed by pointing to a single drop of rain, technically connected, completely inadequate. Which means something else is going on. There must be a source of CP violation that physics hasn't found yet, someplace where matter and antimatter behave differently that we haven't been able to see. And that's what makes what's happening at CERN so important. The experiment I keep coming back to is called ALPHA, the Antihydrogen Laser Physics Apparatus. The goal is almost absurdly ambitious. Build atoms of antimatter, trap them before they touch anything and annihilate, and then study them with enough precision to find any difference between antimatter and matter. If a difference exists anywhere in the universe, it should show up in the spectrum of antihydrogen compared to ordinary hydrogen. Even a tiny deviation, even a gap of 1 part in a trillion, would be a signal, would be the crack that explains everything. Building an antihydrogen atom is not like building anything else. You can't just have the components sitting around, because the moment antiprotons or positrons touch the walls of any container, they annihilate. The ALPHA team has to create antiprotons using CERN's particle accelerators, slow them down to near stillness using a device called ELINA that shrinks their energy by a factor of 100, and then gently coax them together with positrons in a magnetic bottle that keeps them suspended in a vacuum, never touching the walls. The whole process produces a handful of antihydrogen atoms at a time. In a good experimental run, the team might trap a few hundred. I find this detail almost unbearable to think about. Every antihydrogen atom in that trap is surrounded by a magnetic field specifically engineered to be the one thing in the universe that doesn't destroy it. The trap has to be colder than deep space. One vibration too many, one stray magnetic fluctuation, and everything annihilates instantly. The ALPHA team started successfully trapping antihydrogen in 2010. By 2016, they were shining lasers on it. What you're looking for is a specific frequency of light that causes electrons in hydrogen to jump between energy levels. That frequency is one of the most precisely measured numbers in all of physics. If antihydrogen absorbs a different frequency, even slightly, it means the laws governing antimatter are different from the laws governing matter. It means you've found the asymmetry. The result came back clean. Antihydrogen and hydrogen absorb the same frequency of light. The measurements match to better than 10 parts per trillion. On one level, that's an astonishing confirmation that antimatter follows the same quantum mechanical rules as matter down to an almost incomprehensible precision. On another level, it's deeply unsatisfying. Because if antimatter behaves identically to matter at this level of precision, then where is the asymmetry hiding? The universe is telling us every day that antimatter lost the fight. The measurements are telling us they're the same. Those two facts cannot both be true. Something is missing. Here's where I think things get genuinely strange. In 2023, the ALPHA team published results from a new version of the experiment designed to do something that had never been done: measure how gravity affects antimatter. For decades, this was purely theoretical territory. Nobody actually knew whether antimatter fell down. It sounds obvious, but it wasn't. There were serious theoretical proposals suggesting antimatter might fall upward, that gravity might repel it rather than attract it. If that were true, it would upend everything. The experiment was called Alpha G. The G stands for gravity. They built a vertical magnetic trap and released antihydrogen atoms, watching to see which way they drifted. If they fell toward the floor of the detector, gravity pulls antimatter down like matter. If they drifted upward, something wild was happening. They fell. Antimatter falls down. The gravitational acceleration of antihydrogen is consistent with what you'd expect from ordinary matter within the precision of the experiment. That rules out the wildest scenarios. It also closes off one of the last remaining places where some physicists hoped the big asymmetry might be hiding. What you're left with is this picture. Antimatter, as far as we can tell, is a nearly perfect mirror of matter. The spectrum matches. Gravity works the same way. The charge is opposite, which we already knew, but every quantum mechanical behavior we've been able to measure falls within experimental precision of the prediction. And yet the universe is made of matter, which means at some level the mirror is not perfect, and we cannot find where the imperfection lives. The physicist and Nobel laureate Frank Wilczek has described the matter-antimatter problem as one of the deepest unsolved questions in science. That's not rhetorical flourish. It's a precise statement about the gap between what the standard model of particle physics predicts and what the universe actually did. The standard model is the most tested theory in science. It correctly predicts experimental results to absurd decimal places, and it cannot explain why you exist. That is a real, documented failure of the most successful theory ever built. There are extensions of the standard model that physicists are exploring. Supersymmetry predicts partner particles that could carry additional sources of CP violation. Leptogenesis is a theory that the asymmetry was originally created not in matter particles, but in an earlier, heavier type of particle, and only later transferred to the matter we see. The base experiment at CERN is measuring the magnetic properties of antiprotons with such precision that it can test whether any tiny difference exists between a proton and antiproton beyond just their charge. In 2017, BASE measured the proton and antiproton magnetic moments and found they matched to within 1 part per million. Another door almost closed. Almost. That word is doing a lot of work here. Every experiment at CERN is narrowing the range where the asymmetry can hide. And every result that comes back clean narrows it further, which should feel like progress, and it is, but it also means the answer is somewhere the instruments haven't reached yet. Or it means the answer requires physics we haven't imagined. There's a version of this story where the asymmetry turns out to be detectable with the next generation of experiments. The ALPHA team is already pushing toward measurements 10 times more precise than their current best. The LHCb experiment at CERN is studying CP violation in particles called B mesons and finding hints, just hints, of effects that the standard model can't fully account for. Each of these is a thread. None of them have unraveled anything yet. And here's what stays with me. The universe had one job in those first moments after the Big Bang. It was supposed to create equal amounts of matter and antimatter, let them destroy each other, and produce a perfectly balanced, perfectly empty cosmos. Instead, it cheated. By 1 part in a billion, it cheated. And we are the cheat. Every atom in your body exists because physics bent its own rules just barely enough, in ways we still can't fully account for, to let matter survive. The experiments at CERN aren't just answering a technical question about particle physics, they're asking why anything exists at all. That's the question the antihydrogen trap holds. And the most unsettling possibility isn't that we'll find the answer soon. It's that we'll keep narrowing the range, experiment by experiment, and the asymmetry will keep retreating just past the edge of what we can measure, like a horizon that never gets closer. We exist because of something. We just don't know what it is.